Move on to question 2. So in this question, a student is mixing two aqueous compounds here and creating carbon dioxide, water, and then this sodium maleate aqueous salt. And it says here in question A, the student combines equal masses of these two solid chunks with sufficient water at 20 degrees Celsius, and then the student determines 0.0114 moles of carbon dioxide is produced after the reaction is complete. Bit of a wordy question, so just try to underline or highlight key terms. Question 1, calculate the grams of CO2 gas produced. So there's different ways you can do this. I like to use the formula as I showed you in question 1. So I like to use this N equals M over M. We're solving for lowercase m, which is mass. So it's a unit conversion. I'm going to convert moles of carbon dioxide into mass of carbon dioxide. Using the molar mass that I've looked up on my data table provided by AP. So use your AP data table. It may be slightly different than the one you use in class. My answer for the mass of carbon dioxide, 0.502 grams. And I've rounded it to, again, 3 significant digits, which is the amount of significant digits given to me in this mole value up here. So the zeros on the left, those don't count as significant. We're only looking at the 114. Those are your significant digits. All right, so, which, by the way, this value, this many moles of carbon dioxide, these are equivalent values, right? So that's a unit conversion, and we've just turned grams into mole. In question 2, we're being asked again about the carbon dioxide. So it's happening, it was collected at 20 degrees Celsius and it had a pressure of 1.25 atmospheres. Calculate the volume of carbon dioxide in liters. So if you look at the variables that I'm actually given, the best way to calculate the volume is to use the ideal gas law, which is PV equals nRT. I'm going to rearrange the equation to solve for volume. Now, when I solve for volume, so volume will be moles times R times temperature over pressure. So the moles of carbon dioxide were given to me in the previous question. Now, just be careful with your R value. There are a couple of values on your data table. There's an 8.314, but we need to actually use the R value that has atmospheres in its unit. So I'm going to use this one, 0.08. 206 atmosphere liters per mole Kelvin. Okay, and then the temperature, just be careful, it's given to you in Celsius. We need to change this to Kelvin by adding 273. That's our conversion factor, because again, I need my units to be the same so I can cancel things out. And we're going to divide this by the pressure, which is given to me of 1.25 atmospheres. So atmospheres cancels out, moles cancels out with mole, Kelvin cancels out with Kelvin, and I'm left with the answer in liters. Volume is 0.219 liters, again to 3 significant digits. All right, let's do one more problem here before I go into the next video. So this question is saying that the student is, rather than using the chunks of these solids and dissolving those in water, the student grinded them into a powder before dissolving it in water. So the first question is not too bad. What happens to the surface area of the reactants when the student grinds the chunks into powder? Surface area increases. Okay, and that is because of the definition of surface area. If you've ground a solid into a powder, you have more exposed outer surfaces of that compound. So there's more parts of that compound as a powder that are exposed to the water, which will allow it to react with the water. And actually, this will help us answer the next question. So again, it's a little wordy here, but it says here the rate determining step of the overall reaction is the dissolving of the solids. So would the required a time for dissolving of the solids in the second experiment, that's the powder. Okay, so make a note if you forget, this is the powder. Would that be longer than, shorter than, or the same as the time required in the first experiment? This one is the chunks. So the answer to this is we kind of talked about it. It says here to talk about the collisions, shorter than. So it's going to be faster to dissolve the powder. So I'm going to say this is a shorter reaction or shorter dissolving time. And the reason is because with increased surface area, you're going to have more collisions occurring between the solid and the water, okay? Because increased surface area causing your powder to dissolve faster. All right, I'm going to stop here and you can go into the next part to see the answer to question 2 continued.